We'll get started. Awesome. Okay. Hello, good morning, good afternoon, and good evening. Thank you all for joining us today. So today's Research Connection series, first of all, these series are Autodesk Research hosts these series to highlight growing collaborations across our teams and also to showcase the innovative work happening in the industries that Autodesk supports. For all the researchers here, if you have an external speaker you would like to nominate to speak in a future session like this, please fill out a link that I will a form. I'll put that link in the chat shortly for you to take a look. But today we have two amazing speakers. They are nominated by our own Kian Wormsley. A lot of you know him. He's our Director of Systems Design and Architecture Engineering. And I'll hand it over to Kian, who will introduce our amazing speakers today.
Thank you so much, June, and welcome everybody to this session, which I think is going to be absolutely fascinating. So I'm sure you will all enjoy it. So the title is Designing for Crisis: AI, Cognitive Models, and Simulation in the Built Environment. And we have two speakers joining us from the University of Southern California. So we have Dr. Burçin Becerik Gerber is a professor and chair of the Sunny Estani Department of Civil and Environmental Engineering at the USC Viterbi School of Engineering. Her research focus Her research focuses on advancing data acquisition, modeling, and visualization techniques to support the design, construction, and operation of user-centered, responsive, and adaptive built environments. She's pioneered the field of human building interaction, an interdisciplinary field that explores the dynamic relationship between human experience and intelligent built environments. And she's joined by Volkan Ustun, PhD, who is a research scientist at the USC Institute for Creative Technologies and Associate Director of the Human-Inspired Adaptive Teaming Systems Group. After completing his PhD in systems engineering and postdoctoral positions at Georgia Tech and Rice University, he joined USC to pursue research on computational cognitive models for synthetic characters in virtual simulations. His current work focuses on embodied team AI, where he integrates generative AI, including multimodal large language models, with multi-agent reinforcement learning and graph-based representations to solve core challenges in behavioral intelligence and human AI teaming. So with that, I will hand over initially to Burçin, and I'll leave you to take it away. Thank you, Burçin.
Thank you so much for that wonderful introduction. Let me share my presentation and make sure you guys can see it. Does everything look good on your side? Perfect. Thank you, Kian and June, for inviting us. Hopefully we will be able to tell you a little bit about our research and that relates to your work and interest at Autodesk. So Volkan and I met through an NSF project where we're focusing on creating intelligent simulation environments for different hazards, including active shooter incidents. And that's how we got united. And that's what we will be mostly talking about, even though this NSF grant also is interested in fire simulations as well. So I'll start with a little bit of an introduction. As Kian mentioned in my intro, that I am very interested in understanding on how occupants interact with their buildings. And the way that we see this is we look at buildings as if they're machines. I know this is an interesting concept, but we would like to think about intelligent environments that understand you, that can detect your patterns, needs, preferences, and either we design these buildings around the humans or operate the buildings around the human needs. Depending on the type of the building, of course, the goal could be different. It could be learning and effective teaching in an educational building. It could be productivity and comfort in an office building. Could be health and safety in a construction site. So most of my work until a grant before this has been focusing on normal building operations. I was the reason I got interested in this research, as a little bit of a personal touch, was my two kids were in a shutdown in their elementary school because there was actually an active shooter. And I happened to be in London, away from my kids, and receiving all these messages on my way to the airport. In the plane, I said, okay, I need to do something about this. I am a civil engineer. I'm trained also as an architect. I know about buildings, so I really need to study buildings because that's where I can have an effect. So we are very interested in building safety and how we can evaluate building safety, because one of my first research work or focus was like, how can we make schools safer? And I've seen a lot of regulations from FBI and other agencies. What seemed to me like a little bit counterintuitive when it comes to safety during active shooter incidents. So we argue in our work with Volkan that building safety cannot be evaluated without modeling human cognition and behavior. And I will talk a little bit about the simulation tools that we have looked at. But most of the time, traditional approaches focus on physical systems, more the structure, the fire, smoke, and assumes more rational evacuee behaviors and average conditions. We would like to, in our work, we want to think about our work where we integrate human behavior and cognition and capture all that variability, stress responses, interaction with the environment that happens during an unfortunate event like an active shooter incident. So how do we assess a building's performance under crisis, right? I think this work has the assessment of building performance for normal conditions have been quite studied. But when you look at it, something like active shooter incidents, and I acknowledge that maybe this is more of an American problem than a European problem or an Asian problem, but take this as any kind of human-induced hazard condition. How do we go beyond fire and earthquake codes, right? How do we design and operate buildings that are safe for multi-hazards? Because active shooters, fires, earthquakes, multiple hazards can happen in a building or in the course of a building's life. How do we address complex crises like active shooter incidents? And how do we stress test the built environment? Okay. So we looked at simulations. This is earlier. This is where we started. And then immediately our first move was we need to model human behavior under stress. Because current simulations in most cases follow the short or at the time shortest path, move at a certain speed. If there's an alarm, they comply with it and have perfect knowledge of the exits. But in reality, there are multiple behaviors. It's not just run or go to the exit, especially in an active shooter incident. You might exhibit hesitation, there is freezing behavior, you have very limited knowledge of exits. First of all, you don't also know where the threat is, right? Where the shooter is. Is that person close to you or not? Also, on the assessment side, oops, excuse me, I'm not sure what happened there. Let me go back. On the assessment side, there are some certain approaches, but in reality, it's really important to understand when people decide to act, when they believe there's a threat, and how people behave differently, and how the information spreads in a situation like an active shooter incident. So that brings us to modeling occupants' decision-making during a crisis situation, where you have incomplete knowledge about the building. Think about you're in a concert hall, right? You don't necessarily have to be in a building that you work or live. You might have imperfect route choices. You don't always choose the optimal route. And then there is also your decisions could be influenced by stress and limited information. And as I mentioned in the previous slide, you have imperfect awareness of the shooter location. So you can hear maybe gunshots, but you don't know how close they are and not or far. So I'll show you in a few slides what we have done, and Volkan will show his group's approach that we work together. So we try to model dynamic behaviors, and so what I mean by that is even on the shooter side, right? You have to have a harm reduce, and depending on unfortunately, this is a little bit of a disturbing presentation, but the weapon you use, your harm reduced, it changes. You might be exhibiting, or the agents should exhibit, fleeing, sheltering, or remaining in active states. There is definitely a freezing reaction, and then it starts with sometimes freezing and then running and hiding. And then your behavior changes depending on what the situation is. And paths are continuously recalculated in real time in our approach to select safer exits or spaces. So again, this is a little bit of a busy slide, but I have to give you a little bit of background why we have used the tool that we have used, and it's mass motion. And the reason was, with this grant, one of our goals was not to develop something in the research lab that will result into papers, which is great, but the PhD student graduates and the code is not maintained, and we don't have the capacity, obviously, to serve to the designers and the engineers, right, maintain a software. So we wanted to have an off-the-shelf solution that we can work with. So in the end, whatever we develop is actually in the hands of professionals to use. So therefore, we have collaborated with Arup and use mass motion and their Python extensions. Here in this very busy slide, I apologize, that I'm showing you how we have actually modeled the environment, agent definitions, or how we have incorporated risk evaluation and executed the simulation. But I think the most important thing here is that our goal has always been developing on top of a commercially available solution. And sometimes we're very limited what that solution could do, right? In the research lab, we can innovate a lot more. But the goal was to give the tool to the hands of the professionals who will be using this. So this is one of our prototypes. It's a 2-floor campus building. We have also been collaborating here. I should mention Northeastern University's Professor Leboy and Professor Fannin from School of Architecture. In their lab, they have investigated and looked into different school typologies and developed 4 different typologies, because whatever we test, we don't want it to be also very much specific to the building design that we have in hand. So we've been working with these 4 typologies, but you see here one of the agents. What we have implemented is obviously the shooter agent that actually has a goal and searches the classrooms based on that goal. And we have implemented reinforcement learning in our work, where there are rewards and penalties for the shooter. In terms of occupant behavior, we have the run behavior, but we have also implemented hiding behavior. And this hiding or running behavior depends on how close the shooter is, or how close the occupant sense, or the occupant agent sense the shooter to be. We also have a freeze behavior, because I'll talk a little bit about our experts. This research has been very much informed by stakeholders, that we learned that people don't run immediately or hide immediately, right? There's this hesitation moment, and some people actually don't run or hide, just freeze. We have also to evaluate the safety, we had assigned high or low risk tokens, which I will talk in a few slides. So here are some of the things we have done with the active shooter agent. As I mentioned, there is a danger hit. There's a danger radius. So we have implemented in mass motion occupant agents within this range may be shot by the shooter. We're now actually looking at concealment versus complete ability to be able to cover and concealment, and those will actually infuse different levels of risks. We have the shot interval, as I mentioned, depending on the weapon the shooter is using. We also have a hit rate. This is the probability of an occupant being hurt by a weapon. But these parameters can change, and we're able to change these parameters depending on the weapon type, shooter's proficiency with the weapon, shooter's familiarity with the building, and such. Then there are other things that the interactions that we have actually modeled between occupants, the shooter, and the building. Here there are a few of them that I have mentioned in the slide. We have different checks. Encounter check is it determines whether the shooter and the occupants come into contact, which actually triggers the harm mechanism. We have also a door lock status check, because one of the first things that you're told if you have taken any active shooter incident preparedness, that you have to lock the doors. So it checks whether the occupants inside a classroom lock the door and they're protected or not. We have other checks, but these are maybe two examples that I can mention. So let me go to the simulation. I'll just show a little bit of this, what it looks like. Is it playing? Okay, it is playing. It doesn't seem to be running perfectly, but the red one is the shooter. Then depending on the calculation, we have low risk and the high risk occupants. I believe, I don't know if it's running on your side, but I think it's skipping a little bit. It's not perfect. Maybe I try to move it along.
If you can also share again and optimize for video streaming. That might be the problem, but anyway, otherwise we can just skip through.
Okay, so I'm gonna skip through in the interest of time. I think you got the idea, but I'm happy to share the slides if useful as well. Okay, so one of our first questions in coming into this research was, how do we even know about human behavior during a crisis like active shooter incidents, right? It's not like it's well studied. It's not like we have documented incidents. These things happen really fast, and recordings are rare. So we developed a method. We call it elicitation and verification of learning via experts. This is basically bringing all of the experts, from firefighters to policemen to the stress assessment officers to building managers, who have responded to this kind of behavior, this kind of crisis. And we have followed a very strict methodology of like asking them how, if there are two shooters, how occupants would behave. What is FBI agents were there? What are the goals of shooters? And what if it's a two-story building? What if there is if there's an event with parents they don't know, but they're close to their children and such.
I think we have lost Burçin. So, Volkan, if you're able to get ready in case she doesn't come back quickly.
Yeah, I can be ready. I don't know what happened. We are not in the same building with Burçin, so
Maybe we'll just give Burçin a little time to see if she will come back. If not, we'll have Volkan go ahead.
Yeah.
Sure.
Maybe if we can just do a quick, if people have questions, be thinking about questions, because hopefully when we get to the end, we'll have some time for you to ask your questions. And you can also put them in the chat or be ready to ask them in person. It's really up to you. Okay, I think we can maybe assume that it was a computer crash that's
Okay. Burçin says her computer shut down, so she's restarting. But if we wanna, for sake of time, I can start presenting and then we will find a way. I don't know exactly, but
okay.
Yeah.
Let's do that. Yeah.
so I'm hoping you are
Yep.
seeing the presentation, right? Okay.
Yes.
All right. So, hello everyone. My name is Volkan Ustun. I'm a researcher at USC Institute for Creative Technologies, and we are collaborating with Burçin in this project. And I would like to also recognize my student Yunja Wang on the contributions he made in this. And I'm gonna take a little bit of a change of direction over here. And the one of the things that we are interested in doing here is I'm a cognitive behavior modeling. I have a cognition and all that behavior modeling in simulations as my background. And with the rise of large language models, it provided new opportunities for us, especially with the context awareness and things of that sort coming with large language models. We can now think about, okay, we can work on generative social science. In other words, rather than studying existing societies, we can generate synthetic ones populated by language agents. And the interesting opportunity over here is with the large language models, rather than dictating behavior that we want to observe in the environment, we can create a system where we expect these behaviors to emerge with what is already captured or embedded in large language models through their training on large data. So as Burçin started to mention, for this type of a capability, one particular impactful application is high-stakes simulation. So, for example, how crowds behave during crisis situation. These scenarios are often understudied, low resource, and sometimes unethical to create in the real world. However, with large language models, with their innate world knowledge and contextual reasoning abilities, and especially their understanding or their kind of the data that they are trained on understanding how humans could behave or typically behave in stressful situations, we can use large language models as powerful tools to study these domains via the implicit emergence of behavior. And here is we are doing a proof of concept in active shooter instance simulations, and that's basically the basis of my collaboration with Burçin in this project. So one thing that I would like to highlight over here is, as I said, one of the important part over here is implicit emergence of behavior. And when in the last year, there are lots of work on the emotion concepts in large language models. And what we observe that internal representations of emotion concepts causally influence the LLMs out when you use LLMs to generate behavior for you. There's a recent paper by Anthropic basically refers to this phenomenon as the LLM exhibiting functional emotions, patterns of expression and behavior modeled after humans under the influence of emotion. And these could be mediated by different abstract representations of emotion concepts within large language models. My colleague, John Gratch at Institute for Creative Technologies, and his students also did work on these things, understanding the mechanistical interpretability of emotion in large language models and how these large language models align with human judgment and choice. And what we are saying is, observing is emotion is not just in the prompt. It is structured inside the model. And increasingly, we can open the box and intervene and basically provide modifiers or push the model in a certain direction for trigger different emotional responses. And we believe that such causal emotion concepts helps with diversity of behavior to emerge when we use large language models to generate behavior for the generative social societies or synthetic societies that we are trying to create over here. Furthermore, since these emotions are deeply embedded in the large language models, it is possible to trigger human-like concepts like panic or social pressure to emerge from the behavior without explicitly dictating these things. So the second thing that I'm going to look at over here is, okay, we have large language models that can generate behavior for us, but still this has to be anchored by something. And over here, we are going to rely on a common model of cognition, which is basically a functional community consensus, defines a modular architecture that captures the essential structures like perception, motor, working memory, declarative procedure, long-term memories that are believed to be required by the consensus for human-like intelligence. And this common model of cognition basically anchored upon the hybrid cognitive cycle. So humans make decisions at every 50 milliseconds cognitive cycles, and this becomes the bottleneck. And there's the knowledge and skills hypothesis over here, basically saying that intelligent behavior is not purely architectural, but arises from the interaction of fixed mechanisms with acquired episodic and semantic knowledge. And there are also recent affective and metacognitive extensions. So when we are creating our behavior model that would drive behavior of agents in the simulations that we would like to simulate, which is the active shooter instance in our case, we created this behavior model. Basically, we are in our proof of concept model, we use the Unity gaming engine and one of the typologies, building typologies as our simulation environment. And we basically populated this environment with agents, synthetic agents that are controlled by a large language model that is following the behavior model that I'm showing over here. So there is some kind of a navigation system helps the agents to move within this environment and find their ways. And they can communicate with each other via dialogue mechanism. So they can speak and others in the immediate surrounding can hear them, they can communicate that way. And in the agent's black box, in the agent's box, the agents can observe the environment. They have some memory capabilities, and they have a persona, which we basically use this as a diversity or kind of a differentiation between the agents that we have in the environment. Persona is basically their backstory or their experiences from the past, some age, gender, occupation, and personality, some emotion concepts over there could make us a diverse set of agents in the environment. And this is, in a way, similar to or loosely maps onto common model of cognition. Here, our observer is basically the perception mechanisms that our agents have. The navigation system movements and dialogue or speech capabilities are motor capabilities. And the memory and persona serves loosely as the episodic and semantic declarative memories that the agents has. And the LLM planner, where the LLM is basically generating behavior, is where the procedural knowledge and the working memory comes into place, connecting all these pieces, and we can leverage this system to generate behavior for the synthetic agents that we have in this environment. So we use this into work, and we created this Unity-based simulation where we are basically simulating a active shooter instance that's happening. So in this thing, all the students and teachers are going with their day. And on the 2D sketch on the top left, you will see a red circle enter the building, and that's our active shooter. So this active shooter is basically a script following a scripted behavior, and it basically goes through the building, and when it sees somebody in the environment, it basically shows. This is a very basic simulation of this thing. And we can run these simulations and collect information on how things are emerging or what type of behaviors that these agents are exhibiting in this environment, and we can run these simulations. But more interestingly, we can do additional stuff over here to check whether some of the things that we are interested in are actually in place over here. So on the left, we are seeing the same room simulated when the agents basically have no active shooter training whatsoever. So they are basically behaving on a plain or standard condition, and some of them are hiding and some of them running away. And what we can do is we can kind of do some kind of an after action review with the help of these large language models. We are basically storing all the context and the rollout of the simulations. And after the fact, we can ask the agents that synthetic characters in the simulation what they have done, some kind of an after action review or an interview, why they have done certain things and what they have done and what they were thinking. And this is, again, I'm not necessarily saying that large language models are actually following all of these reasoning steps, but it still kind of provides a lens into how those agents are making decisions and what affects their decisions and what is the emergent behavior that we are seeing over here. On the right side, what we have done is we provided a training manual as declarative knowledge to some of these agents. And what we are seeing is a shift in behavior. So basically now more agents are running to the exit and trying to get out of the building because that is what the manual says. And when we are asking questions to these agents, they basically take hints from this guidance and what the ASI handbook says, and basically that shows a shift in their behavior while they are trained by this manual, or when you provide additional information, additional context, it has a genuine impact or shift in their behavior. And this is something that we wanted to observe, and this allows us to run different experiments with different conditions and see whether those things are impactful in the behaviors that we are observing in these simulations. But this opens up another question. All right, so now when we are in the plain condition, when we run these experiments, we observe a certain behavior distribution. But as Burçin was mentioning in the Evolve workshop that we run, when we talk with the subject matter experts, their expectation, their output behavior, the behavior distribution that they are kind of expecting in these situations is different than what we are observing in our own simulation runs. So that basically is the research question that we were asking in one of the papers that we recently published at EMNLP conference is, okay, how can you close this behavioral realism gap? So how we can basically change the observed behavior of the synthetic characters in these simulations and match with the expectations of the subject matter experts in this without explicitly dictating them what to do. That is basically the research goal or research question that we have asked. And for this, we developed a behavior alignment framework. So what we are doing is we are basically going through iterations with the help of large language models. And we are looking at the observed behaviors in the simulated distribution and look at the differences or divergence from the expert distribution or expectations of the experts, calculate the realism gap, and then use this information to change the personas of the agents that we have in our simulation to generate new characters with new background stories, new personalities, or making basically changes in the personalities of these characters, and run this thing again and see whether we are still whether we are getting closer to the reality or expectations of the SMEs, or whether there's still a divergence. So we do this for a few iterations. I mean, I think we've done 5 or 10 iterations on this with the help of large language models, and we showed that we can actually update or via updating the personas of the agents that we have in our simulation, we can close this behavior realism gap. So to show the results, we basically run 3 cases where there is no enforcing, which is our baseline. We did explicit enforcing, basically saying that certain percent of the agents should be exhibiting certain behavior, and we explicitly stated large language model to do that. And the implicit enforcing is the framework that I have shown you. We are basically going through iterations, updating the personas of the agent and trying to match the expected behavior that is stated by the subject matter experts that came out of as a result from that Evolve workshop that Burçin mentioned. And what we are seeing is with the PIVO or PIVA persona evolvement behavior alignment framework, we can actually close this gap. Explicit enforcing is still shows a better match to the reality or the expected distributions, but the framework can get really close to that. And one different thing is, as I at the beginning of thing, we want to have this behavior emerging implicitly out of the changes that we are making to the agents. This is important for us because the explainability things that I was showing and other things, when we explicitly say, okay, this is doing the explicit enforcing thing, when you ask agents why you did certain behavior, the answer comes out to be because you told me so. Or it is basically because I had to fit to this distribution, therefore I have chosen this distribution. You lose that context awareness capability that comes with this implicit emergence or implicit modification of the behavior or personas in the simulation. So this is, in a way, this evolve iteration framework that we introduced over here is a more consistent and explainable, and in several cases, it can even outperform explicit enforcing while also maintaining much better contextual realism. So that is basically the main outcome of this study. Furthermore, when we look at the results and the personas under the hood, we see that there's a close match between our expectations, what type of personalities should be showing what type of behavior, and what type of persona features or personality characteristics have an impact on the choices of the behavior selections and things of that sort. And we run basically a TF IDF analysis on this and group different cell-line features that of the personas that's showing certain behavior, and we can argue that there is a strong correlation between the features that we are expecting to show certain type of behavior and those agents are showing that type of behavior. So when it is a freeze behavior, one of the salient feature is that agent tend to be overwhelmed easily, and that is one of the personality characteristics of those agents, and they are generally with context awareness, they are showing the freeze behavior. But this doesn't necessarily tell that they always show that behavior. If a character or synthetic character has this getting overwhelmed as a personality trait, but during the simulation that agent is straightened very close to the exit, that agent still gets out of the building. This personality characteristic does not necessarily dictate all the behavior. They have some contextual awareness, but in general, we can have a close correlation between how we are changing the personas and the behavior that they are exhibiting in these simulations. Another thing that we looked at over here is whether this evolved personas can be transferred. And we ran a test where we are moving these agents that we trained in one environment to a new environment. So here we basically transferred them to a new office building without re-optimization, and it still kept that alignment, behavior to realism alignment to a certain extent. It is, of course, it's not as aligned as if it retrain these things, this population of agents from scratch, but still transfer keeps some of that alignment in the system, and it's significantly better than the no enforcing baseline case that we have. So we also run a bunch of different experiments for convergence and cost in large language models. I'm just gonna skip those things that are all available in the paper. Now, what we are doing. So Burçin mentioned there are 4 typologies, building typologies that we have. So we are basically trying to leverage those typologies, and we are creating a completely new pipeline in the Unreal Engine. We selected this for a bunch of reasons that I'm not going to get into details, but we are using this new system that we are building for a rigorous validation of the behavior model that we have generated and this behavior alignment framework. So basically the idea is to collect different videos for different use cases and try to give subject matter experts to chance to interact with these videos, to observe different things, and providing them maybe after action review chances to actually talk with the agents that are seeing in this environment, so that they can do an in-depth analysis of the behavior that they are observing and whether they can validate or provide hints about whether this behavior matches with their expectations and could be a realistic behavior that could be used in these simulations. And moreover, we are trying to situate or anchor this validation study with different type of conditions, or as we call them, awareness conditions, like what type of occupants that we have, how the behavior changes if the population, some of the population is children or children with parents or just adults. Whether you know the shooter or not plays a role in the decisions that you are making. Whether familiarity with the environment or the building, it affects your behavior or not. And if it is changing your behavior and we are expecting it to change, it matches with the expectations of the subject matter experts, how that behavior should change. And also this whether any kind of trainings, ASI trainings or information about these active shooter incidents, again, the same thing, how that behavior changes if that information is provided to these agents, and whether those changes, shifts in behavior matches the expectations of the subject matter experts in these type of situations, and we will use these interviews or analysis to try to further validate our framework can generate valid human behavior that could be used to simulate these active crisis or high stakes simulation conditions. So that's all I have for today, and thank you for listening. I don't know whether Burçin came back or not, but
I'm back. I'm back. I apologize for on behalf of my computer decided to shut down, and it took quite a bit. But I didn't have a lot of slides. If Volkan, if it's okay, maybe I show a couple more slides and we open it to Q&A. I was almost in the end actually.
absolutely.
So I'll try to if you can unshare, I'll share my screen.
I just did.
Thank you. Hold on. And hopefully I won't have any more hiccups. Okay, it's going extremely slow, so I am not 100% sure if this is going to work, but we'll see. If you lose me, just go to Q&A. But this is where I was, and Volkan mentioned the evolve method a couple times. This is what we base some of the decisions we made, as Volkan explained very nicely in LLM, but also in the mass motion side. I think one important thing, he alluded to this as well, Validation of this kind of work is also very difficult because we're running these simulations, and my $1,000,000 question to my students is if this happens in the real world, how close we are, right, to the results, because this is really a high-stake evaluation of buildings, and if we want to evaluate different design decisions or different implementations within a building, we want to make sure that we're correct. So it's one way of doing this is looking at past incidents and trying to replicate those. But as I mentioned, the data is very scarce in those kind of situations. And even if the same incident happens in the same place, you don't know if the results are going to be the same. So our way of doing this, as Volkan mentioned, is asking subject matter experts. So we have also run multiple workshops, bringing our different simulations, as you can see on the slide, reinforcement learning, mass motion that I mentioned, LLM that Volkan explained, and running them very methodically and asking SMEs like, do you see anything odd? Does this make sense? Would you expect this behavior? And getting their feedback and iteratively revising these simulations until we get to a point they say this sounds realistic. Let's run it one more time, or let's run it in this what if scenario and see if we can get that same kind of accuracy or expected behaviors. So our goal is translating results into design decisions, right? The layout, the visibility, access or egress decisions for these kind of crises. Or how do we implement alerts or signage, or how do we provide guidance? Or can we use these simulations for training or running some protocols in the building or doing drills? So our stakeholders are here, architects, designers, of course, emergency planners, policymakers, regulators, different authorities, facility managers, and operators. And everything you see there are actually people that we have asked for validation or for in the evolve methodology. But there are open challenges. I think some of these challenges Volkan's method, LLMs are addressing, but they're still open. I mentioned this many times, the data scarcity in extreme events, validation of human models, and I explained to you, and we can have a discussion how else we can do this. There are also ethical considerations and risks. So if we have to make sure that whatever we're running and whatever we're providing as results are sufficiently accurate, right? Because we don't want designers to make decisions or develop something with false confidence in safety. And they might have serious consequences for real buildings and real occupants. So I'll leave it there. I will unshare. I had a few more slides, but I don't think they're important in this case. And maybe we can have a Q&A.
Thank you so much, Burçin and Volkan. It was a fascinating topic and really, really interesting. If you have a question, please raise your hand, and we can ask them. Take advantage of having them with us live. Maybe I'll just get started with one while well, actually, Mish, go ahead. Your hand is raised.
Sure. Oh, sure. Thanks. Great presentation, like a really fascinating subject. I was just curious, sort of in looking at the way you guys are doing the simulations and the modeling for these situations, are there interventions that you're looking at building design that are more active? So what I'm getting at more specifically is training, say, vision models or something like that to do early detection of these situations. I know that raises also possible a lot of other concerns, but I'm just curious if that's something you're thinking about, and if that changes how you think about building design and thinking of buildings as these machines in the kind of age of AI that we're living in. Thanks.
Yeah. Early detection of shooters, you mean, Mesh?
Yeah, or just obviously, like if a shooting scenario starts, there's a propagation phenomena to it, I guess, where if something's happening, you have a way of creating responses in the building, alarms, something external. There's a lot of ways I guess I could go with.
Yeah. Yeah, so I think there were a few design decisions we have looked into and we want to look into. Those were, I mean, we looked at in one study like automated locking or different locking mechanisms of doors, right? And how those would result. We looked at different exit locations within a building. We're looking at what happens if there are doors connecting different classrooms, or what happens if there are doors opening outside, right? People can run out. We looked at different broadcasting mechanisms, alarms, or information dissemination. We want to look at, there were recommendations about having curved corridors, for example, in these schools so that the line of sight is interrupted for the shooter. So we want to test what happens if it's straightforward one or a curved one, or what happens if you stagger the doors of classrooms. But anyway, but these are some of the design decisions. I personally have not investigated what happens or how we can stop the shooter or with early detection. My focus have always been on the design side and providing that feedback to the designers.
Thank you.
Hey, Mike, you have a question?
Yeah, thanks for the great talk. You've kind of answered my first question about what kind of design considerations you have, kind of like things like modifying lines of sight. Kind of makes me think about bastions in like old star-shaped forts back in the day, where the defendant would have a much better line of sight. So I guess you've kind of answered that question already. But I was also wondering, since you mentioned, active shooters are most likely in the United States. I was wondering if there were any thoughts, considerations, or simulation with regards to simulating occupant behavior, such as fighting or shooting back, and those kind of possible scenarios.
Fighting or shooting back. We haven't gotten to that, but there are some fight behaviors that we have implemented. Actually, SMEs told us that if you, for example, have a veteran or somebody with that background, they're very likely to actually fight or in an occupation very similar to that. So we have implemented some fighting behavior. We have implemented also in some of our simulations, which I didn't show, how to improvise different weapons, right? Using, mundane objects and what happens in those cases. But I think also another challenge here is these buildings have to be designed and operated for multiple hazards, right? So that's where we brought the fire example, because it's really well codified. I haven't shown anything, but something that works for fire, active shooters must also work for fires, right? So that's where we got into multi-hazard discussion, because you can't design these buildings just for one hazard or one crisis. You have to design them for multiple crises. Sorry, I answered a little bit of a different question, but that's where we stand right now.
Great, thanks.
I think I have a question that's probably for Volkan, but it was around the training of the agents, of the LLMs. Is that kind of done by modifying the personas and giving them certain behaviors or skills, or do you actually you point the LLMs at some sort of online training and have them
No, it is
follow?
basically primarily done by persona modification. So if in a way, with the LLMs, we are saying that if, for example, freeze behavior is underrepresented in the output behaviors, then we are basically injecting personas or changing certain personas that would be more in line with freeze behavior. So that changing the agents, the personas of the agents that we have in the building population, and then we rerun the simulation and observe the exhibited behavior and see whether we are actually closing to the expected behavior or there's a distance or a difference between them.
I see. I was thinking more specifically about the ASI training that's done. Is it the same answer
Oh,
for that?
okay. So for ASI training, that's one of the conditions or kind of a early validation things or early testing of our model. So when we were doing this, we were curious about, okay, how the behavior would shift if these agents have prior knowledge about this ASI situation. So as a site test case, what we have done is for a trained population that we have, to some of them, we provided this ASI training as additional information. So we are keeping all the personas intact, but some of the people in the classrooms or in different environments, we are providing this additional information on ASI training or handbook. Basically, there's an ASI manual training book somewhere. We just provided this thing as context to the LLM in addition to all the persona information. And we observed the behavior of these agents after they have this training. What we are seeing is the exhibited behavior now shifted towards what is said in the ASI handbook, and they are more inclined running out, even though their personas is saying something else. If they see an opportunity to run out of the building, they run out of the building because that's what they remember from the active shooter manual, basically. So this is kind of a early validation test. We were trying to see whether if you provide this additional context, whether that's going to shift the behavior in the way that we want this to shift the behavior, and whether that could be used for enhancing the analysis of such systems that we are developing.
Okay, that's fascinating. Essen, you have a question.
I know we have the time, but once again, thank you so much for the lovely presentation. I was wondering, with the simulations you ran, there was the LLM-based one in Unity as well as the mass motion. Could you also talk a bit more about the reinforcement learning-based one and how it kind of compared related to the other ones and whether it was kind of a different approach?
So that was an earlier work, SN, and we trained the shooter using reinforcement learning to have certain goals. Unfortunately, I know more than I want to know about these events and the shooters, but we learned that there could be they're either looking for a person and they're basically going classroom by classroom or room by room until they find, but they harm people in their way, or their goal is harm as many people as possible because they have some kind of a issue or problem. So that was all about like how do we train this shooter agent using reinforcement learning, right? Maximizing, unfortunately, a very terrible thing of harming other agents and penalizing them by shooting wrong or going to the wrong classroom. So it was that, and we brought that or we're bringing that to mass motion now. So not only the occupants have intelligent behavior, but also shooters also have intelligent behavior.
Just a quick note on that. I mean, the reinforcement learning is used for shooter behavior, and it could be, it can function very well over there. But when we try to apply reinforcement learning to a large population, like 80 to 100 dwellers or occupants in a building, and we want them to exhibit different behaviors, that reinforcement learning training gets really messy in the multi-agent reinforcement learning case. So we have not done it. Conceptually, it could be done, but it is a really computationally messy training.
Good point.
There's a question in the chat. If I'm, Burçin, if you are seeing it.
Yes. The simulations as training ground for those who are intent. Yeah, I know. That has been actually a question. Yes, so that goes back to the ethical considerations, right? So what happens if these simulators are in the hands of shooters and they use it for training purposes? Yes, that could happen. I don't have a good answer for that. That was not something I thought about when we started this work. But I'm assuming they're training one way or the other, right? So I'm not sure having a simulation or not would stop the training process, unfortunately. But the goal was also one, maybe I didn't mention that if we can, so I mentioned a lot of designers and engineers who are making decisions for the built environment. But one of the other goals we have is to give this solution to the responders, emergency responders, so that they can run some what if scenarios. What if there are two shooters? What if they come in the afternoon? What if they come during a weekend? What if they go to a building and then another building, so that they can train to respond effectively to these kind of situations? But again, those ethical considerations are always on the table.
Yeah, just to follow up, by no means was that meant to sound like a criticism or a challenge to the work. It's just, it is an unfortunate thing. Those that are intent on doing harm can find a way to do harm. And just wondering how we're red teaming it from both sides. So thank you very much. And again, not meant to be a criticism. I really do
No, it's okay.
appreciate the
I think it's a
thoughtfulness
valid
and how you
point.
guys went through it.
Thank you.
And it's a valid point, and I mean, it's not in the context of what we are discussing over here, but conceptually, you can approach this from an adversarial perspective, and a game theoretic equilibrium search can be conducted on these things. What type of behaviors can be game theoretic equilibrium and can be successful against the different types of shooter profiles and things of that sort, but we are not yet doing that in this line of research.
Okay, I think we are a little over time, so we should probably call it there. Thank you once again, Burçin and Volkan, for a fantastic presentation. Again,
Thank you, Kim
really,
and June,
really
for inviting
interesting.
Thanks for
us.
having us.
And extremely
feel free
relevant
to
to our
send-
research.
And I will put my email address here. If anybody has any follow-up questions, please feel free to do that.
Okay.
Thank you so much, Burçin. And I want to thank all the researchers and residents in this call. It might be quite late for some of you, but thank you so much for joining us. And also, thank you to our amazing speakers for such an informative and inspiring presentation.
Thank you.
Okay.
We appreciate the invite.
Thank you.
Bye-bye.
Bye.
Thank
Bye.
you.
Thank you.
Bye.
Thank you.